Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic, delay unit. In our previous topic, we have done with the area capacitance of layers and sheet resistance. So based on these two parameters, we are going to calculate delay unit. That's a continuation topic for the previous two topics, sheet resistance and area capacitance of layers, where we have summarized both sheet resistance and area capacitance of layers based on the layer information into their respective tables with their relative values. So in the present lecture, we will be focusing on delay unit based on the sheet resistance concept and area capacitance of layers. After completion of this lecture, you will be able to compute the expression for delay unit based on sheet resistance and area capacitance of layers. As we have discussed in our previous class, the wiring up of the circuit takes place through various conductive layers during MOS processing. So we should be aware of resistive and capacitive characteristics of each layer for electrical analysis. So in this scenario, the sheet resistance and standard unit of capacitance are the two important parameters which will be helpful in evaluating various effects of wiring in which one of the effect is delay unit. So the table what you are viewing here is the typical values of sheet resistances for various technologies from 5 micrometer technology to 2 micrometer to 1.2 micrometer technology, where the values are given in terms of ohm per square. So here the one square represents where width and length are equal. As we have discussed in our sheet resistance topic, a resistance value for a square layer is independent of area of the square. So based on that concept, so for a metal layer, if that is a 5 micrometer technology, and for a given square layer, the resistance would be 0.03 ohm per square. If that is 2 micrometer technology, 0.04 ohm per square. If that is 1.2 micrometer technology, that is also 0.04 ohm per square. So one more parameter we will look into. See the cell parameter, this one if we take, this corresponds to an N transistor channel, that is N MOSFET, and that is relevant to 2 micrometer technology, which is showing a sheet resistance value of 2 into 10 power 4 ohm per square. Right, hope this is clear. So similarly, we have the tabulation for typical values of area capacitance also. So as we have discussed in the previous class, these were given in terms of picofarad per micrometer square multiplied by 10 power minus 4. For example, if I take this cell into consideration, that is shown as 0.33, this represents the area capacitance between metal 1 and substrate for a technology of 2 micrometer is 0.33 into 10 power minus 4 picofarad per micrometer square. So whose relative value is 0.04. So this relative value is from when we divide this 0.33 with the gate to channel capacitance 8, we get the relative value as 0.04. Hope that is clear. And capacitance, we have discussed the standard unit of capacitance also, that is a capacitance for a feature size, that is a W is equal to L, that is for a standard square. This we have discussed in our previous topic. So this is one of the example for capacitance calculation. So when you consider the layer that is shown here as a metal, so the capacitance to substrate calculation is given here. Relative area multiplied by the relative C value. Relative area is a direct calculation from the layer information. whereas relative C value you should take it from the table based on the material what you are interested in. Then you will be getting the capacitance value in terms of standard unit of capacitance. Similarly with polysilicon, similarly with diffusion also. Hope this is clear. So coming to the delay unit. See, delay unit is tau. So in this terminology, we are calling it as delay unit. But in general, this is similar to how you calculate your time constant in your electrical circuits of RC circuits. Time constant is given by R into C. The same formula will be applicable to the delay unit denoted as tau. So consider the circuit shown here. This is the case when one standard gate area capacitance. So this is one standard gate area capacitance is being charged through one feature size square of n channel resistance. So this is the n channel resistance of one feature size. So in both the cases, this is W is equal to L. Here also that is W is equal to L. So how this capacitance is being charged by this resistance. So such measure is given by the delay unit. In normal terms, we call it as time constant, given as tau is equal to Rs of n channel, that is sheet resistance of n channel, multiplied by standard unit of capacitance in seconds. So if you evaluate it for 5 micrometer technology, see tau is equal to, so sheet resistance of an N channel MOSFET for 5 micrometer technology is 10 power 4 ohms, and standard unit of capacitance for 5 micrometer technology is 0.01 picofarad. So when we multiply these two, the time constant or delay unit will result in 0.1 nanosecond. If that is a 2 micrometer technology, the sheet resistance for N channel is given by 2 ohms, 2 into 10 power 4 ohms, and whereas the standard unit of capacitance is 0.0032 picofarad. So the delay unit in turn will be 0.06 for nanoseconds. That is a product of sheet resistance and standard unit of capacitance. Similarly, for 1.2 micrometer technology, the sheet resistance is 2 into 10 power 4 ohms and standard unit of capacitance is 0.0023 picofarad. Product of these two will result in the value of tau, that is time constant known as delay unit, 0.046 nanoseconds. So now the tau values that were obtained for various technologies through the concept of delay unit are not much different from the transit time what we have calculated in our unit 2, that is voltage and current relation, the very second topic of MOSFET. So there we have calculated tau SD, electron transit time, as L square by mu into VDS. This is a known formula to us. So if you substitute the typical values of length of the channel, so if I consider a 5 micrometer technology, so length of the channel is 5, so L square will be 25 micrometer square divided by mu n. So typical value of mobility of electrons is 650 centimeter square per volt second, and VDS, the average value of drain to source for N channel MOS is 3 volts. So when you substitute these typical values and evaluate, you will be ending up with the transit time as 0.13 nanosecond, which is not much different from the calculation what we have made just now through sheet resistance and area capacitance as 0.1 nanosecond. So this is very close to the theoretical time constant that has been calculated above. Right? Hope this is clear. So based on this topic, there are few lecture level problems to be discussed in our classroom. That's all for this topic. Thank you. Happy learning.